Welcome back, dear students. Moving charges and magnetism, quick revision session part 2. Today we are going to discuss Ampere's circuital law and its applications. First, Ampere's circuital law. The line integral of magnetic field over a closed loop is equal to mu 0 times the net current flowing through the conductor. So consider a conductor where current flows from bottom to top, I ampere current. Then a closed loop. This is an imaginary loop. This loop is known as Amperian loop, just as Gaussian surface in electrostatics. Here it is Amperian loop. It is a closed loop. So due to the small current element dl, magnetic field at a distance r, this is closed loop. Then magnetic field closed integral B dot dl is equal to mu 0 I. This is called Ampere's circuital law. Then closed integral dl. This dl integrating over the circumference of the circle. Then you will get b into 2 pi r is equal to mu 0 I. Then b is equal to mu 0 I by 2 pi r. This equation we have already studied. This is the equation for magnetic intensity due to an infinitely long straight wire at a distance r from midpoint O of the conductor. So first application of Ampere's circuital law is current carrying solenoid. So the given figure represents a solenoid. The number of turns of the coil coming out of the plane, and here it is into the plane, and number of turns wound on a common core. The given core is air, so it is an air core solenoid. Let us see, there are two sets of angles are given. First one is theta 1 and theta 2. These two angles are taken from the axial line, and from this point to here it is theta 1 and this one is theta 2. And the other two angles are alpha and beta. They are taken from the distance r from edge of the solenoid to at a point on the axial line. So these angles are alpha and beta. So number of turns from the relation B is equal to general equation for magnetic intensity due to the solenoid is given by B is equal to mu 0 Ni by 2 into sine alpha plus sine beta. Sine alpha plus sine beta. If we consider alpha and beta here. If alpha is equal to 90 degree and beta is equal to 90 degree, then magnetic intensity along the axial line is obtained. Then we can say that B axial sine 90 is 1, 1 plus 1 is 2, this 2 cancels with this 2, so B axial is equal to mu 0 Ni. This is the general equation for magnetic intensity along the axis of a solenoid. Okay, then from the second equation B is equal to mu 0 Ni by 2, taking the second set of angles, then it will be cos theta 1 minus cos theta 2. This is the derived equation. So the same axial point is obtained by taking theta 1 is equal to 0 and theta 2 is equal to 180. So theta 1 0 means this point, this line is here, and theta 2 180 means this line reaches here. So along the axis of the solenoid, B axial becomes mu 0 Ni by 2 into cos theta 1 cos 0 1 minus cos 180 minus 1. So minus of minus 1 gives plus 1, 1 plus 1 2, this 2 cancels with this 2, so B axial is equal to the same equation mu 0 Ni as above. Okay. Then the next case from these equations, at one end of the solenoid. At one end of the solenoid, see the point P lies here, then alpha becomes 0, then beta is equal to 90 degree. Alpha is equal to 0 degree and beta is equal to 90 degree. This is the condition for magnetic intensity at its one end. Then the equation becomes B is equal to mu 0 Ni by 2 into sine alpha, that is sine 0. Sine 0 is 0 plus sine 90 1, that means mu 0 Ni by 2. This is B at one end of the solenoid. So we can write B axial is equal to 2 times B end, or B end is equal to half of the axial magnetic field. So this is the magnetic intensity due to a solenoid. Okay, here what is N? N is known as number of turns per unit length. If total number of turns is 1000 or 2500 are given for a length of 50 centimeter or 20 centimeter in the question, then we have to take the number of turns per unit length. So N by L, say 1000 by 50 or 100 by 25. If the length and number of turns are given in the question, then you have to take the number of turns per unit length. Okay, the next application of Ampere's circuit law is magnetic field due to a toroid. So this toroid is given here. So current enters from this end and rotates in the anti-clockwise direction and comes out. So the center of the toroid is taken as O, and R is average radius. Here R is equal to, if we take the outer radius are R1 and inner radius R2, then R is equal to R1 plus R2 by 2. This is the average radius of the toroid. Then magnetic field due to the toroid is only along the axis of the toroid. Axis of the toroid is dotted lines, green dotted lines given here. So B is equal to mu 0 Ni. This is the magnetic intensity due to a toroid. Here we consider 3 points O, P and Q. At these 3 points, magnetic intensity is measured. At O and Q, there is no field. Only field lines present along the axis of the toroid. So BP is equal to mu 0 Ni and BO is equal to BQ is equal to 0. What is N? Here N is equal to, for a toroid, N is equal to number of turns by 2 pi r, N by 2 pi r, where r is average radius actually. It is given by r1 plus r2 by 2. If outer radius and inner radius are given in the question, then you have to consider r by taking the average value and substitute here. So next application of Ampere's circuit law is current carrying thick wire. So let us consider a current carrying thick wire of radius A which carries a current I ampere, and 2 ampere loops are considered, one inside the conductor which is here drawn here, which has radius R1, and the second ampere loop is outside the conductor with radius R2. Then magnetic field due to a current carrying conductor B dot dl is equal to mu 0 I by Ampere's circuit law. Inside the conductor, B closed integral B dot dl is equal to mu 0 I dash, because I dash is the current flowing through the inner Amperean loop. So we have I is equal to J dot A, that is J dot pi A square, or I proportional to A square. So I dash proportional to small r square, then I dash by I is equal to r square by A square. From this point, B dot dl, closed integral dl gives 2 pi r1 for the conductor of radius r1, that's equal to mu 0 I dash. Then B is equal to mu 0 I dash by 2 pi r1. Let us then substitute, this equation is 2 and this is 1. Substitute 2 in 1, we will get B is equal to mu 0 by 2 pi r1, I dash by I. So I dash is r1 square, so hence it is r1 square by A square. Then I dash is equal to I r1 square by A square. So we will get mu 0 I by 2 pi A square into this r1, and r1 from here cancels and remaining r1. So this is the answer. So as we move from center O to the surface of the conductor,
B directly proportional to R or B proportional to R. So this is very important. Inside the conductor, B directly proportional to R. Then what is the magnetic field outside the conductor, which is closed integral B dot dl is equal to mu 0 I due to magnetic field due to the outer ampere loop is due to the current flowing in the actual conductor, so that B into 2 pi R2 is equal to mu 0 I. So B is equal to mu 0 I by 2 pi R2 or B inversely proportional to R. So we can say that inside the conductor magnetic field is directly proportional to R and outside it is inversely proportional to R. Then distance versus magnetic field of a thick wire. See, distance is taken in the x-axis and magnetic field in the y-axis. Center O of the conductor, then B is directly proportional to R from surface to center. So this point is A, surface of the conductor. Center to surface is directly proportional to R and outside it is inversely proportional to R. So B inversely proportional to R. B inversely proportional to R graph is a hyperbola. Here it is a straight line. This is the graph of magnetic field due to a thick wire of radius A. Okay, here all the distances are measured from the center. It is very important. Okay, let us solve a problem from this session. Consider a thick wire of radius A which carries a current I ampere. Then ratio of magnetic intensities at distances A by 2 above and below the surface of the wire is. So here a conductor of radius A where all the distances are measured from the center, then a point above the surface which is A by 2 distance from the surface and below the surface which is also A by 2. Then you have to take two ampere loops. One is inside the conductor which is at a distance A by 2 from the center, that is taken as R2, and above the surface it is A plus A by 2. From center to this point this is 3A by 2, A plus A by 2. So B1 is equal to mu 0 I by 2 pi R1, that's equal to mu 0 I by 2 pi 3A by 2, that's equal to mu 0 I by 3 pi A. And second B2, inside the conductor it is mu 0 I by 2 pi A square into R2, where R2 is A by 2, 2 pi A square into A by 2, A square A cancels, and then mu 0 I by 4 pi A. Ratio of intensities means B1 by B2, that's equal to mu 0 I by 3 pi A into 4 pi A by mu 0 I, mu 0 I, mu 0 I, pi A, then 4 by 3.
Next, Lorentz force. We know that there are two types of Lorentz forces, which are the electric Lorentz force and magnetic Lorentz force. Electric Lorentz force simply F is equal to QE, that is the electrostatic force, and magnetic Lorentz force is F is equal to Q into V cross B. F is equal to Q into V cross B. So total Lorentz force is the sum of electric Lorentz force and magnetic Lorentz force. Here we can take the magnitude as QVB sin theta, because V cross B is VB sin theta. Consider a positive charge plus Q is placed in a uniform magnetic field. Initially the charge is at rest. So first case, the charge is at rest, that means V is equal to 0. Then what will be the force? In the QVB sin theta, V is equal to 0 means F is equal to 0. In the second case, if the charge is projected with a velocity V, but the projected velocity is along the direction of magnetic field, that means theta is equal to 0 degree, therefore F is equal to 0, because sin 0 is 0. And the third case, if the charge is projected with the velocity V and anti-parallel to the direction of magnetic field, this charge is projected anti-parallel to the direction of the field, then also force becomes 0 because sine 180 is 0. And in the fourth case, if the charge is projected with a velocity v other than at an angle other than 0 or 180, then it experiences a force. That force is magnetic Lorentz force QVB sine theta. So theta other than 0 or 180, that means F is equal to QVB sine theta. Then fifth case, if the charge is projected at right angles to the direction of magnetic field with a velocity v, that is theta is equal to 90 degree, therefore F will be maximum, that maximum force is QVB. Next, what is the direction of motion of the charge? Say if we project the charge with a velocity v at an angle theta, then it will follow a helical path. So this is the helical path. It will follow a helical path. This is the path of this velocity vector, and if we resolve in this direction, this is v sine theta, and this direction v cos theta. Then what is the pitch of the helix? Pitch of the helix is equal to, that is x, that is displacement along x-axis. This is known as pitch of the helix. Then pitch of the helix x is equal to v cos theta, component of velocity along x-axis, into time, because it is a displacement, hence it is component of velocity into time gives displacement. So pitch of the helix is v cos theta into t. Okay, if the charge is projected at right angles to the magnetic field, then maximum force is obtained. Then trajectory of the charge will be a circle. So if the charge is projected with a velocity v at right angles to the magnetic field, then it will follow a circular path. Then the necessary centripetal force for the charge is provided by magnetic Lorentz force. So v square v cancels, then v is equal to qbr by m, and r is equal to mv by qb. So radius of the circular path r directly proportional to velocity of projection. If a positive charge is projected at right angles to the magnetic field, then Lorentz force will be maximum. So the trajectory of the charge will be a circle. So the necessary centripetal force for the charge is provided by the Lorentz force. This is the theory of cyclotron. So the necessary centripetal force mv square by r is equal to qvb. So F is maximum, then v square v cancels, so v is equal to qbr by m. This is the velocity of the charge, and radius r is equal to mv by qb, that's equal to p by qb. P is equal to root 2 me, where E is the kinetic energy of the charge. Then R is equal to mv by qb. Here we can write R proportional to v for a particular charge. Radius of cyclotron is directly proportional to velocity of projection. That means if we project a charge with a small velocity, then the radius will be very small. If we project with a large velocity, then the radius will be very large.
Next, cyclotron. Cyclotron was invented by Ernest Orlando Lawrence. It is a particle accelerator used to accelerate charged particles like proton, deuteron, alpha particle, etc. to high energies. Cyclotron consists of two semicircular hollow spheres. At their center, a source of positive charge is placed. When the source emits a positive charge, then because of the alternate positive and negative charges of the D's, it attracts and repels the charge between them. Hence, it is accelerated due to a high magnetic field present inside the D's. Then it is accelerated to the target. Then the necessary centripetal force for the charge is provided by the magnetic Lorentz force. Here magnetic field is so arranged that the magnetic field is always perpendicular to the direction of motion of the charge. That means QVB sine 90. Then maximum Lorentz force is obtained. Then mv square by r is equal to QVB. Then v square v cancels. Then r is equal to mv by qb. This is called radius of cyclotron. And velocity is equal to qbr by m. This is the velocity of the particle of charge q and mass m with a magnetic field b. This applied magnetic field is represented by b. So velocity of projection is directly proportional to r. This equation we have already studied in Lorentz force. Then kinetic energy. Kinetic energy is equal to half mv square. That is half m into q square b square r square by m square. This m and m square cancels. Then q square b square r square by 2m. This is the equation for kinetic energy of cyclotron. Then time period of cyclotron. Time period t is equal to 2 pi r by velocity. Circumference of the circle divided by velocity, that is 2 pi r by, what's the velocity? qbr by m, that is qbr divided by m. R and r cancels, then it is 2 pi m by qb is the time period of cyclotron. Then from the time period we can obtain frequency. Frequency is equal to 1 by t, that is qb by 2 pi m. qb by 2 pi. These are the equations from this topic. Next, the limitations of cyclotron. Cyclotron is a particle accelerator. It can accelerate only charged particles. That's the first limitation. Neutron-like chargeless particles cannot be accelerated in cyclotron because it works under the positive and negative charges of the oscillator. So chargeless particles cannot be accelerated. Then electron has charge but it cannot be accelerated in cyclotron. That's also a limitation. Because of the least mass of the electron, it will escape between the gap of the d's when it attains some energy from the source. So while accelerating the electron, it becomes electromagnetic wave. So here radius of cyclotron is very important equation, because r is equal to mv by qb, which can be written as p by qb. P is the momentum, mv is equal to p, and in terms of energy it is 2me by qb, because E is kinetic energy is equal to p square by 2m, or p is equal to root 2me. From this equation we can write root 2me instead of p, therefore root 2me by qb. Let us solve a problem from this session. Three particles, a proton, a deuteron and an alpha particle, are simultaneously projected with same kinetic energy at right angles to a uniform magnetic field B. Then what is the ratio of the radii? Then three particles, proton means 1h1, deuterons means 1h2, alpha particles mean 2he4. So these particles are projected. Then R with same kinetic energy, then it is R is equal to root 2me by qb, or R proportional to root m by q, because they are projected with same kinetic energy in the same magnetic field, right angles to uniform magnetic field. So R proportional to root of m by q. Then R proton is to R deuteron is to R alpha particle is equal to root m proton by q proton is to root m deuteron by q deuteron is to root m alpha by q alpha. Then what is the ratio? Mass of proton 1 root 1 by charge 1 is to root 2 by 1 and is to root 4 by 2. That is 1 is to root 2 is to 1. Okay. If they are projected with the same velocity, then what is the equation? Now the equation becomes R proportional to, or R is equal to mv by qb, then R proportional to m by q. Because V is constant, we are projected right angles to the uniform magnetic field, then B is constant, then R proportional to M by Q, then R proton is to R neutron is to R alpha is equal to M proton by Q proton is to M neutron by Q neutron is to M alpha by Q alpha. First one, 1 by 1 is to 2 by 1 is to 4 by 2, that's equal to 1 is to 2 is to 2. Okay. The same question we can solve in the case of same momentum. If three particles are projected with same momentum, the same particles, then equation becomes R proton is to R neutron is to R alpha is equal to 1 by Q. That is R proportional to 1 by Q, because same momentum means P constant, same magnetic field, therefore B constant, then R proportional to 1 by Q. Then 1 by Q proton, 1 by 1 is 2, then 1 by charge of neutron, 1 is to next 1 by charge 2. So 1 is to 1 is to 1 by 2 means 2 is to 2 is to 1, right?